For you. Alright, cool. So, example 24, here we go. Let's set up our givens. What?
Does like the text show up on the...
What do you mean? He's taking a video.
No, but it's like...
This camera's like 10 years old.
Yeah, exactly.
No, man, it's good.
Alright, man.
You guys are even older than that. Alright, givens with units. Here we go. We have a cannon firing a cannonball. There is a way to approach these problems. We just did the cannon and the ball yesterday, and the cannonball problem is actually what we call a conservation of momentum problem. The givens kind of give it away. So 1,000 kilogram cannon, the mass of the cannon is 1,000 kilograms. The mass of the ball is 50 kilograms. Now who's going 90 meters per second? Whose velocity is that? That's the velocity. Wait a minute now. Better read it over. It fires a 50 kilogram cannonball at a velocity of 90. So whose velocity is that? The ball. The ball. The velocity of the ball is 90 meters per second. West! Put west positive because it's going to matter. Put west positive because it's going to matter. Now, determine the recoil velocity of the cannon. So we watched that little video from the hallway. The cannon definitely had a velocity afterward. Let's figure it out. Now in your reference table, there's an equation for this. It's called the law of conservation of momentum. It's just written like this. P before equals P after. That's all it is. Now before and after what? Before and after what?
Good question.
It is a good question.
Before and after the launch.
The launch, the explosion. Before is, this really means before explosion. That's when you have your cannon here with the wheels and the ball is still inside. After, of course, is after the after the explosion, which looks like this. The ball is heading this way, and the cannon is actually heading this way slowly. That's after. In fact, because of this nice method, this law of conservation of momentum, we don't have to worry about during the explosion. All we have to worry about is before and after. Some point before, some point after, we can put this together. Watch what happens. How many objects do we have before? There's the cannon and the ball. So what you can say is, before anything explodes, there is the momentum of the cannon, and there is the momentum of the ball, and the way we account for those two together is we add them. So the addition of the momentum of the cannon and the momentum of the ball before goes on this left-hand side. Now many of you already know the answer to this. In fact, you're allowed to know it. What's the whole left side going to be equal to already? Huh?
The right.
Yeah, of course, equal to the right. Numerically, what's the left-hand side going to equal? Think about it. What's the momentum of the cannon and the ball before it explodes?
0.
0. This whole left side is going to be 0. You're allowed to know that. But we're giving you the full setup right now, and you'll see substituting how you get that too. After the explosion, we still have two objects. Each one has some momentum. We've got the cannon, and we've got the ball, and those two are added afterward. Got this so far? So look what we did. Law of conservation of momentum, before and after. And now we're just going to look individually at the pieces involved. How do you solve for momentum? Simple equation. What's that, Laura?
M times V.
M times V. So for this, we can just write the mass of the cannon times its velocity before, plus the mass of the ball times its velocity before, has to equal the mass of the cannon times its velocity after, plus the mass of the ball times its velocity after. Now this is just a very formal way of writing what we already discussed yesterday and already wrote in with that tennis ball and the cannon there. So far, is this okay? The law of conservation of momentum, break it into the two objects involved, which for our problems will generally be two objects. And then just how do you individually get them with their M's and V's. Now I could give you a problem, like on the homework you'll see, where I make it easy for you actually. One of the givens is P of, let's say, the gun. And they tell you what it is. Well, then you know it already. You don't have to do the M and the V. This problem doesn't have that, though. All right, let's start plugging and chugging. The rest is details. Mass of the cannon, 1,000. We already have our units here, so I'll just write this. What's the velocity of the cannon? Ooh, what's the velocity of the cannon? Oh my, 90x. Oh my goodness. You got to organize your brain to this little chart. This is the velocity of the cannon on the before side. So it is 0. Immediately that goes away. Plus the ball, 50 kilograms, times its velocity. What's its velocity? Be careful, you know what people want to put in there, right? You want to throw that 90 in there, but you have to sort your brain to say this is before the explosion, so it's 0. Boom, goes away. Equals mass of the cannon. It's still 1,000 kilograms. Do we know its velocity over here? That's its velocity after. That's actually the question mark. That's what we're trying to get. So we're going to leave that as the velocity of the cannon. Plus the ball, which we know is 50 kilograms. Times, do we know its velocity? That's the 90 meters per second west because it's on the after side. Okay, now let's just do a little algebra here. This became 0 plus 0 is 0. You can put units on it if you want. Kilogram meter per second. Equals 1,000 VC plus 50 times 90. You don't need a calculator. There you go. 4,500 kilogram meter per second. Now you got that one? Now, people mess up this algebra step all the time. They're like, oh, it's nothing here, so I'll just ignore this whole left side, and that's not an equation. You need the 0 on this side for this to be an equation. You got to solve for VC. So of course your next move, take 4,500 from both sides. That goes away. And you're left with negative 4,500 equals 1,000 VC. Your final move? There it is. And cutting this one out puts a decimal. Your final velocity of the cannon is negative 4.5 meters per second, which means negative is just our choice. What does this actually mean? 4.5 meters per second? East. East side. Okay. There it is. Does that make sense? The ball heads 90 westward. The cannon, so the small mass ball, the big mass cannon heads 4.5 the other way, eastward. Reasonable?
Sir.
I mean, the big mass should go at a small speed, and it should go the other way. So in that regard, it's reasonable. And then, this is how you do it. Good. Cut that.